This is Inconel. It's one of the toughest and most heat-resistant materials that we use to build rocket engine. It melts at 1300 degrees Celsius. But inside a rocket engine, temperatures usually get to 3000 degrees Celsius. So what's stopping the engine from melting? The answer, the fuel cools the engine before it burns. Let's start with something familiar to all of us. How does a car engine work?
So the fuel burns in the engine, creates hot expanding gases that causes the pressure buildup in the engine and which pushes the piston.
Yep, so you mentioned those hot expanding gases, right? They're pretty neat, but they generate a bit of excess heat. And we can't just leave that excess heat there. It has to go somewhere. So what we do as engineers is we use a coolant. We take that coolant when we pass it around the engine block. It grabs all that heat, and once it's heated, we move it to a different element. That element is a heat exchange element. That heat exchange element is what we commonly call as a radiator. Yeah, a radiator.
Simple system, works on the ground.
Yeah, pretty simple, pretty ingenious. The thing is, rockets don't have radiators. There's just no space for them. And the amount of heat a radiator needs to mitigate from a rocket engine is simply too large for it to handle. So the other thing about it is rockets keep moving through the atmosphere, so it might not work too well for us.
So Suyash, what's the solution?
The solution is kind of simple. You use the fuel as a coolant. You have it with you, might as well use it.
Before it burns.
Yeah, before it burns. So the thing is, we have different types of fuels. Sometimes it's liquid hydrogen, sometimes it's liquid methane, sometimes it's kerosene, sometimes it's hypergolics. And the one thing that unites all of them is that they're good coolants. So you take that and you pass it through hundreds of tiny channels along the periphery of the engine. And these channels, they run from the nozzle end all the way to the combustion chamber end.
Oh, that's smart. So the fuel, while it runs along these two channels, is absorbing the heat.
Yeah, it's absorbing the heat and it's keeping the metal cool enough for it to survive the full duration.
So the fuel is doing two jobs, as a coolant and as a fuel.
Yep, you're right. So it gives us two advantages as well. The one we've just talked about, of course, right? This cools the engine. The other one is, as you heat the coolant a little and then you dump it back into the chamber, what happens is you get a little bit kick out of it. And as it does so, we get a little more efficiency out of it.
So this is what regenerative cooling means. Nothing wasted.
Exactly. Nothing's wasted. Physics works for you, not against you. Let's see if we can understand this a little better. Alright, let's do this. So I'll start by sketching out the rocket engine, and I'll be a little crude about it, so don't judge me. So, pretty simple looking rocket engine. Now, essentially, what we're going to do with this rocket engine is we're going to slice it. We're just going to cut across it like this. And as we do that, what we're going to see is like an inner wall over here, which is typically very thin, just to allow for good heat exchange. And post that, what we're going to see is the sections of our channels. Now these channels, they don't need to be a fixed width. They can vary in widths as we go along. There's no requirement for us to keep them the exact same. And another thing that I'm going to do so that it's easier to follow is I'm going to section across here. So let's just look what that looks like. So it's just going to look like a circle. By the way, this is what we call as the throat of the engine. All right. And so you'll just see two concentric elements and you'll see channels.
So it's printed within the metal.
Yep. It's all integrated in one go. And
So why is that the shape? There is a convergence and a divergence, right? What's the significance of that?
yeah, that's a good question. So this is what is known as a de Laval nozzle. It's something that helps us generate thrust. It's one of the basic principles of engine design. And we'll talk more about that in the coming episodes too. So the fuel typically enters here.
You meant typically there are other cases as well?
Yeah. So it's not always a requirement that you make it enter from the nozzle end. Sometimes, depending on your need and how the design is set up, you can make it enter here. You can make it enter midway. There's nothing stopping.
There's no hard and fast rule for that.
Exactly. We have to design it to meet our needs, right?
I have one question with channels. How do you make those tiny channels in the wall,
Right.
engine wall? Yeah.
That's a good question. Now these channels are very small, and yeah, they can be 1 mm small. How do you make them? Earlier, when technology was not as well defined, well developed, we used to have a lot of processes, a lot of headache used to go into making them, and months on end to deliver a finished good. But today, with the magic of 3D printing or additive manufacturing, we print this in a single go, layer by layer, and it's all integrated into a single element. So essentially, what you're looking at is, at the core of it all, is the combustion chamber. And this is where we have your 3000 degrees Celsius hot gases, and they're going to be ejected out of this nozzle over here. Now as the fuel enters, it passes through the full length, right? And then it has to exit somewhere.
Oh, that's where it absorbs the heat and it exits.
Exactly, this is where it's gonna do all the business, and it's just gonna exit here, and then we're gonna dump it back in. Now when we dump it back in, we use a different element per se, and we call that the injector, right? The injector is the device that essentially sprays that fuel and the oxidizer into the combustion chamber. They mix in the chamber and they ignite, and the process continues.
Yeah, would that channels make it typically structurally weaker?
Right, so that's a good question. They're pretty small, right? And you might think that, hey, this thing is operating at really high pressures, there's really high temperatures, so it might not be wise to put holes along the length. But think of it this way. Think of pillars in a museum. Those multiple pillars are supporting the weight of the roof. So you have to be well calculated about it. You can't space them too far apart, but you don't want to keep them too far near to each other.
There's a margin.
There's a limit wherein you want to operate, and that's where the designs,
The geometry matters.
the geometry matters, and we do thermodynamic calculations, CFD, all of that stuff to find out which.
What's the
space-
CFD?
CFD is computational fluid dynamics. It's a field of fluid dynamics wherein we study and model how fluid flows through channels or tubes, pipes, etc. All right, so I hope this explains a bit about regenerative cooling and brings you all clarity.
Yeah, it's good to see what goes inside from what we see outside.
Yeah, pretty cool. Okay, so the wonderful thing about this is not just on paper. This is real things that we do on near daily basis. Every time we fire a Raman 2 engine, we have regenerative cooling principles being applied and tested. So we look at the cooling performance and we see where the temperature is doing well, where it's not doing so well, where it's optimum, where it needs changes, so on and so forth.
But why wouldn't it be not uniform?
Right, so there's always the off chance that sometimes there's a foreign object debris that ends up coming and blocking the channel. These channels are sub-millimeter level kind of scale, so they're not too hard to block. Now of course we can take care of external debris, but what about an internal debris? So that's always a possibility, and there's always a possibility of non-uniform combustion occurring as well. So the goal is you need to keep on working through it.
And what happens if let's say there is a channel blockage and it's not uniform?
Right, so in case that happens, what happens is the heat transfer to the metal gets restricted, it disrupts the flow, and once that flow is disrupted, the local temperature in that region goes higher than the melting point, and that can cause a catastrophic failure of the engine.
Oh, so we have to remake the engine and do the test all over again?
Yeah, that might sound like a bad thing, which in some cases it is, but since we additively manufacture our engine, we have a little more leeway, and what we can do is we can iterate faster, we can come up with multiple designs to see what works, make changes, and test it again in a matter of days. Worst to worst, maybe weeks.
And without additive manufacturing, how was it done previously?
Right, so they had it pretty tough. Sometimes it used to be months if you were having good days in months, but if it didn't go as per plan, if there were failures while manufacturing itself, then it can be years before you actually see hardware. And then think of it this way, you test that engine, something's still not working, and then you're still stuck. You have to make a brand new engine, and that takes even more time, months again.
So this regenerative cooling isn't just one size fit all design, right?
Yeah, it's not. The good thing is designers have a good control. We looked at the schema earlier, and we said we can change the number of channels, we can change the height of channels, the width, the transitions, we can do all of that. So the designer has to think and apply first principles to select something that works well thermodynamically and gets the best cooling performance in all zones. So by doing this, we can tune all aspects of engine design and get the best performance possible. So I hope you understand in good detail what regenerative cooling is, how it helps us make great engines that run for the full duration without melting. So that was regenerative cooling. It solves a brutal problem of managing extreme heat by offering fuel a side gig.
It's an elegant design, but it only works if you know what's happening at every stage.
True.
That is Flow State, a free-flowing conversation about rocket science and more, where we dig into ideas and innovations powering Skyroot.
Next up on Flow State, we talk about nozzles. How do you direct all that hot combustion gases and make them generate thrust? Because that's where it gets really counterintuitive.
Garden hose physics meets rocket science.